Okay, well, it's 10 to 2, so let's start. So, our first speaker this afternoon is Sonia Balan from the University of Manchester, talking about Emmy Noether's Ascending Chain of Abstraction.
Hi, thank you so much. Thank you for the introduction, and I'm so happy to be here. And thank you for those who joined. Today, I want to talk about a woman who faced the impossible. You might have heard the name before, Noether's theorem, Noetherian rings, but the names of theorems couldn't quite capture the life behind them. She was born in 1882 in Germany. At the time, women were not allowed to teach properly and enroll at university. When she first attended lectures, she had to ask each professor individually for permission just to sit in the room. Despite this, she passed the entrance exam, and in 1904 she enrolled at the University of Erlangen. She was the only woman studying mathematics there. She completed her PhD under Paul Gordon on invariant theory in 1907, and in her thesis alone, she computed 300 invariant expressions by hand. Her work soon attracted the attention of two mathematicians who don't need an introduction, David Hilbert and Felix Klein. They invited her to Göttingen. In fact, David Hilbert asked her to help resolve a mathematical paradox from Einstein's theory of relativity, what later became known as Noether's theorem. And by the way, what is now known as Noether's theorem was actually just a preposition in the paper. In this talk, we will focus more on her 1921 paper, Ideal Theorem Rings, where I will introduce the notion of Noetherian rings. But despite work of this importance, she was not allowed to hold a teaching position. For years, she lectured under Hilbert's name because women were not allowed to teach officially. When the faculty objected to her habilitation, Hilbert famously responded, "We are a university, not a bathhouse." One of Noether's colleagues, Hermann Weil, later wrote in his obituary that her strength was to strip away the essentials so that the whole could be surveyed. And in this spirit, I invite you on a small journey to this forest of abstraction, where we begin with familiar trees, and at each step we will move to a more general structure. And each time we increase in abstraction, another tree will appear on the slide. And our goal is to see how far and how deep we can go into the forest, because before Noether's idea stops working. Let us start with something familiar. Divisors in the integers. Take the number 3. For one, there's the fact that if two integers are divisible by 3, then their difference is also divisible by 3. Cool. Once more, if a number is divisible by 3, multiplying it by any other integer keeps it divisible by 3. So multiples of 3 behave nicely. They are close under subtraction and stable under multiplication. But of course, only so much you can do with arithmetic. This is why mathematicians abstract these properties into special sets that sit inside of rings, ideas. We see that ideas capture exactly the same properties that we observe for ideas, and in some sense, they are kind of like the algebraic version of the divisors. Now, let's go back and look at some examples of ideas in the integers. The multiples of 12 form the ideal 12z, but every multiple of 12 is also a multiple of 6. Every multiple of 6 is also a multiple of 3. Every multiple of 3 is also a multiple of 1, right? So we reached the whole thing. Can we go further? You're probably nodding. So yeah, exactly. In the integers, this process must stop. And what we just saw, it's an example of something called chain of ideas. And in the integers, chains like this, again, cannot continue forever. Emmy Noether realized that this idea is incredibly powerful. Whenever chains of ideas cannot grow forever, the ring has a kind of finiteness built into a structure that makes it structurally similar to the integers. And obviously, we have the tools to study in the integers, so it just makes the whole thing easier. So this property is called the ascending chain condition. Rings with this property, this condition, are called Noetherian rings. And now you might ask, and rightly so, apart from the integers, which are kind of like the canon integer, which rings are Noetherian? And we now turn to one of the most important families of rings, at least in my opinion, polynomial rings. A polynomial ring consists of finite sums that look like this, where coefficients are from a ring and we attach a variable to them. And naturally, we wonder if the coefficient ring R is Noetherian, what happens when we add a variable? And for this, to provide some context to this, we turn back to the history. So in the late 19th century, invariant theory, so what remains unchanged after some transformation, and in our case, Noetherianity, the ascending chain condition, invariant theory was extremely computational. Then in 1890, David Hilbert proved something quite remarkable. And instead of computing generators like by hand, as Noether did in her thesis, Hilbert proved that the finite generating set for every polynomial ring from coefficients from a field must exist. So in other words, it means that every polynomial of a Noetherian ring is Noetherian. And that's huge. So in other words, that means that Noetherianity survives when we add a variable in a sensible way. And what I mean by sensible way, sorry, I forgot to, that was actually intentional. So what I mean by adding a variable to a sensible way is this. In ordered polynomial rings, something very convenient happens, something that I think you took for granted, which is that your variable commutes with your coefficient. So x times r equals r times x. But in my talk and in my year 3 project that this talk is based on, I asked what happens if we remove this assumption. So if our coefficient ring is Noetherian, does this still hold when multiplication becomes non-commutative? And surprisingly, in many cases, the answer is yes. And here we start our journey deeper and deeper into the forest, meeting some kind of wild constructions that surprisingly are still Noetherian if the coefficient ring is Noetherian. Now, suppose the variable interact with the coefficients through some rule that twists the multiplication. The simplest example is this, where alpha here is just a rule that rearranges the elements of the ring. It's an automorphism of the ring. And surprisingly, even with this twisted multiplication, we still obtain a very well-behaved polynomial ring. And as I was about to say, if the coefficient ring is Noetherian, then this ring, skew polynomial ring, is still Noetherian. Now, we can twist things even further. We can allow negative powers of x, producing what is actually called a skew Laurent polynomial ring. And again, if R is Noetherian, the coefficient ring, then this ring remains Noetherian. We can even introduce something called basically a derivation, something that resembles differentiation into the multiplication rule. These are called formal differential operator rings. And yes, they form a ring. And yes, if the coefficient ring is Noetherian, then yes, this is still Noetherian. Okay. If all these twisted constructions still preserve Noetherianity, what is the most general polynomial ring we can build where multiplication is non-commutative? And does it still pass the test of the basis theorem? Well, the first word here is polynomial. So the elements must still look like polynomials. In order for each expression to represent a unique element, we require that two polynomials are equal only if their coefficients agree. Okay, this is quite harmless, just like to establish some order with existence. Now there is another property which we usually take for granted when it comes to degrees. When we multiply two polynomials, we require that the degree of the product should not exceed the degrees of the sum of the degrees. Sorry. So it's just this relation here. And to reinforce this rule, it is simple enough to understand what happens when you take the simplest polynomials like elements, the variable x and the constant polynomial r, the coefficient. Since the degree of x is 1 and the degree of r is 0, by plugging these things in, we require that the degree of x times r is no more than 1. And because this x times r is still a polynomial in itself, we can just naively write it like this, like a degree 1 polynomial. And because these little r's depend on our r from the left-hand side, they're functions of r, we can coincidentally call them alpha and delta. Now we still need this structure to behave like a ring. We need it to be a ring. By requiring multiplicative identity and distributivity, we force these functions to satisfy certain rules. For example, we have some initial conditions, and for distributivity, we basically require them to be additive maps. Now, what surprisingly offers us the most information, for once, surprisingly to me, is associativity. Again, I did this in my project. I'm not going to do it in live here. But again, by naively identifying coefficients from the first term and last term, we get the relation for alpha to be this. So it's an endomorphism. And for our delta is this. And it still kind of resembles a differentiation, but kind of twisted by alpha. So it's an alpha derivation, conveniently called. And yeah, this is the minimal conditions that we require in order to build a general skew polynomial ring, again, where multiplication is non-competitive. And remarkably, the same phenomenon happens again, except we need to establish some order in some way. So again, if the coefficient ring is Noetherian, and alpha is not only an endomorphism, but it is an automorphism, so an injective endomorphism, then we still get that this Q polynomial ring is Noetherian. And it's quite remarkable to me, because even at this level of abstraction, this finiteness property survives, and no matter how much we twist the multiplication, Noetherianity can persist. So now we have reached the deepest part of in the forest, and this is where our journey ends. And it's quite huge to me that Emmy Noether created such a strong framework for understanding ideals that it tames even the most kind of wild structures. Like, we basically had to stop where we were met with the axioms of algebra. It's kind of cool to me, like however far we push this algebraic machinery, we strip away the essentials, as the code said. You retain a structure that's worth like studying and well behaved. And I guess rings are just way behaved constructions like this. This is why I like them so much. So we end where we began. But remember, it was Noether who figured all of this out. The same Noether who built this abstract framework was once a student who needed permission just to attend lectures. The same Noether who once worked unpaid for years. The same Noether who could not present her own work at conferences. The same Noether who later taught in her apartment after she was banned under Nazi laws. The same Noether who fled to the US, where she was also denied a teaching position at Princeton because she was a woman. And the same Noether whose life unexpectedly ended at 53 years old. And I just want to end by kind of opening a question that Emmy Noether's story reminds us that brilliance should not have to fight this much in order to exist. I mean, today the doors are more open than they were in Göttingen in Germany at the time, but are they wide enough? Just pay attention to whose voices fill the seminar rooms, and notice whose names are attached to the theorems we study, and ask who feels permitted to imagine themselves at the center of this discipline. And again, I leave you with a question: is the room shared yet? Thank you.